Have you ever found yourself trying to get up to speed on some complex new tech,
Mm.
and you just feel like you're drowning in jargon and, endless
It's
articles?
absolutely, it happens all the time.
It's such a common challenge, right?
Yeah.
And it's exactly why we do these deep dives. So today, we're going to try and cut through the noise, understand a really fascinating breakthrough in AI.
Okay.
We're talking about large language models, LLMs, and, their amazing ability to translate languages. English to Spanish, great. But what about, like, all those other languages?
Yeah, the ones that don't have billions of web pages backing them up.
Exactly. Especially those with fewer digital resources. That's where things get, well, tricky.
Precisely. And that's our mission for this deep dive.
Yeah.
We're digging into a pretty groundbreaking research paper that introduces something called LLaMAX.
LLaMAX, okay.
Yeah. The paper's title is LLaMAX, Scaling Linguistic Horizons of LLM by Enhancing Translation Capabilities Beyond 100 Languages. Bit of a mouthful, but
Yeah. Sounds like a research paper. All right.
it is. But the core idea is how this model tackles these big hurdles in translation, especially for those lower resource languages. So our source today is really excerpts from that paper.
Gotcha. And this really matters for you, the listener, because think about it. Better multilingual AI could just dramatically reduce language barriers.
Definitely. Global communication could be way more seamless.
Right. And access to information becomes, well, truly universal, no matter the original language. LLaMAX could really change how we all interact with AI.
Yeah, it's potentially huge.
So, okay, let's unpack this then. We've all seen LLMs do impressive stuff with, say, English and Spanish translation. It feels pretty solid.
Mm-hmm.
But where do they actually struggle? What's the core problem LLaMAX was built to fix?
Right. So the main issue the research tackles is this gap. They work great with high-resource languages, yeah, but their performance in low-resource translation is, well, often pretty suboptimal.
Suboptimal meaning. Just not very good.
Yeah, often not usable, frankly, and it's a big barrier. The main reason seems to be just not enough multilingual data when they're first trained in that pre-training phase. They just haven't seen enough examples of, say, English to Swahili or Yoruba to Vietnamese.
That makes intuitive sense. The paper actually has a figure, right?
Okay.
Figure 1 that shows
Yeah.
this, especially for something like Arabic.
Exactly. Figure 1 shows the translation directions hitting a certain quality score. It's called SPBLEU, just a way to measure translation quality on a test set called Flores 101.
Okay.
And what you see is most models are kind of clustered near the bottom for Arabic-centric translations, like Arabic to other languages or from other languages to Arabic. But their performance for English-centric translations is much, much better. So even for a major language like Arabic, there's this significant gap compared to English.
Wow. Okay, so it's not just obscure languages.
Not at all.
Yeah.
And people have tried to fix this,
Yeah.
fine-tuning existing models, training new ones from scratch, making language-specific LLMs.
Yeah.
But these often cover only a few languages, or the performance still isn't quite there. The problem needed a different angle.
Okay, so given that challenge, how did the LLaMAX creators actually tackle it? What were their key strategies? Maybe some surprising ones.
Yeah, they really zeroed in on two main technical things. First, how the model handles its vocabulary, like the words it knows.
Okay.
And second, how they augmented the training data,
Yeah.
especially for those low-resource languages.
All right, let's start with the vocabulary. You said it was counterintuitive.
Yeah, this part is really interesting. The common sense idea, right, is if you want a model to know a new language, you just add a bunch of words from that language to its vocabulary. Expand it.
Seems logical. Add more Italian words to make it better at Italian.
Exactly. That's the assumption. But what LLaMAX found, and this is in Table 1 in the paper, was that adding even a small number, like just 100 new language-specific tokens, actually hurt the model's overall multilingual performance.
Heard it.
It degraded it. And adding even more new tokens just made things more complex, needed more data, and didn't give the payoff you'd expect. It kind of, messed with the model's existing balance.
So throwing more words at it wasn't the answer. That is surprising.
It really is. So the breakthrough was realizing they should actually stick with the original LLaMA vocabulary.
The one it already had.
Yeah. The original LLaMA models use something called a byte-level byte-pair encoding tokenizer, or BBPE. And they found that just using that was the most cost-effective and robust way to scale up to over 100 languages.
Why? Why does sticking with the original work better?
Well, this BBP tokenizer is super efficient. It basically breaks text down into sequences of bytes. Since any text in any language can be represented as bytes, it means the tokenizer works universally. You don't need an unknown token for unfamiliar words.
Ah, okay. So it handles everything right out of the box.
Pretty much. It optimizes how the vocabulary is shared across all these different languages.
Mm.
There's another interesting angle. It helps keep English working as a kind of internal pivot language.
A pivot language, like it translates everything through English internally.
Sort of, yeah. Studies suggest LLMs often map inputs toward English representations before generating the output in the target language. Sticking to the original vocabulary helps maintain that internal structure effectively.
Fascinating. The paper also mentioned something called fertility. What's that about?
Right, fertility.
Hmm.
It's basically the ratio of how many tokens the model uses compared to the length of the original sentence. Like how many pieces does it break the sentence into?
Okay.
And they found a really strong negative correlation, like negative 0.88 Spearman coefficient, which is high between fertility and the quality of the model's internal representation. That's in figure 5.
Negative correlation. So lower fertility is better. Fewer pieces.
Well, adding new tokens does reduce fertility. It makes fewer pieces. But the key finding was that this reduction didn't actually improve the model's ability to generalize linguistic patterns across languages.
Ah, I see. So even if it used fewer tokens, it wasn't learning the underlying language connections any better.
Exactly. It's like, simplifying something too much might make it seem easier, but you lose the nuance needed for real understanding, especially across many languages.
Okay, that makes sense. So they stuck with the original vocabulary, but they still had the problem of not enough data for many languages, right? How did they fix that?
Right. That's where the second part comes in. Data augmentation. Specifically, dictionary-based data augmentation.
Dictionary-based, like using bilingual dictionaries.
Precisely. Because getting real parallel sentences, human translated pairs, is super hard for low-resource languages. So they found a clever way to create pseudo-parallel data, artificial pairs.
And what did they find was important here? Like, did the type of dictionary matter? They mentioned MUSC or PanLex.
Yeah, good question. They found that the choice of dictionary really mattered, and its effectiveness correlated directly with the number of unique words or entities it had for the target language. That's in Table 2.
So a bigger dictionary for that specific language helped more.
Basically, yes.
Wow.
More coverage meant better pseudo-parallel data could be generated.
And how did they generate it? Figure 2 shows something.
Yeah, Figure 2 illustrates it. They'd take a sentence in a higher resource language like English and then strategically replace some words with their translations from the dictionary into the target low resource language. Creates a sort of synthetic parallel sentence.
Clever. And they looked at one-hop versus two-hop translations. What's that?
Right. So one hop is just looking up the word directly. English word, target language word. Two hop would be like translating the translation again, maybe through another language.
Okay. Seemed complicated.
And it turned out simpler was better. Tables 9 and 10 show that one hop was generally sufficient. Doing the two hop thing sometimes actually made performance worse. Probably introduced too much noise or errors.
Interesting. Keep it simple.
Seems so. And one more detail on the data, how they formatted it. They found that connected parallel worked better.
Connected parallel.
Yeah, instead of treating the source sentence and the generated target sentence as two separate pieces of text, split parallel, they just concatenated them into one single data point, connected parallel.
Huh. Like just sticking them together.
Essentially, yeah. And Table 11 shows that this simple trick actually gave better translation results. It's amazing how these seemingly small details in data prep can make such a difference.
No kidding. These are genuinely fascinating technical choices. But, okay, the proof is in the pudding, right? What did all this mean for LLaMAX's actual performance? How good did it get?
Right, the results. And they were pretty impressive. LLaMAX achieved significantly higher translation performance compared to other existing open source LLMs. We're talking more than 10 SIPS-P BLEU points improvement on average.
10 points. That sounds like a lot in translation metrics.
It is. It's a really substantial jump. You can see the comparisons in tables 3 and 4. And what's more, it performed basically on par with highly specialized, very large translation models like Facebook's M2M112B model, at least on that Flores 101 benchmark.
Wow, on par with a specialized giant. That's huge for an open source model.
Absolutely. It really validates their approach.
Okay, so it's good on the test set. But what about languages it wasn't explicitly trained on? Could it generalize?
That's a fantastic question. And yes, that's one of the most exciting findings, I think. When they tested it on a different benchmark, Flores 200, which includes even more low-resource languages, LLaMAX showed significant improvements even for languages it hadn't seen during its augmented training.
Really?
Yeah, Figure 4 shows this. It demonstrates this really strong generalization capability. It means the model learned underlying linguistic patterns, not just memorizing the pairs it saw. It can handle unseen, long-tail languages better.
That's crucial for real-world use. I mean, what about the original model's abilities? Did teaching it all this translation stuff make it forget how to do other things? That whole catastrophic forgetting problem?
Ah, yes, a classic concern when you continue training a model.
Yeah.
But the good news is LLaMAX seems to have avoided that. It maintained its general task performance in English pretty much level with the original LMA2.
How do they test that?
They use standard benchmarks. Things like MMLU for factual knowledge, BVH for complex reasoning tasks, HELLA-SWAG for common sense. And the scores were very similar to the base LLaMA2 model. Table 5 lays this out. So no real compromise on its core English capabilities.
That's great. You get the translation boost without losing the general smarts. Okay, now, the comparison everyone wants to hear. GPT-4. How did LLaMAX stack up?
Right, the big one. So as you'd probably expect, LLaMAX 2 generally trailed GPT-4 when translating between high-resource languages like English to French. GPT-4 is just, enormous and trained on vast data.
Sure, makes sense.
But, and this is the kicker, in low-resource translation contexts, the very thing LLaMAX was designed for actually outperformed GPT-4.
Whoa, really? Outperformed GPT-4?
In those specific low-resource scenarios, yes. Figure 6 shows this comparison. It was a massive win, I think, for accessibility and for anyone needing translation for less common languages. It shows specialized open models can really compete, even beat the giants in specific areas.
That is a huge deal. Okay, so it's a great translator, but is it just a translator, or can it do more?
That's another key point. It's not just a translator. It's positioned as a robust multilingual foundation model, meaning it's a better starting point if you want to then fine-tune a model for specific tasks, even in English, but with multilingual awareness.
How so?
Well, they found it gave an average improvement of about 5 points over the base LMA2 when fine-tuned on tasks like cross-lingual Q&A, XCSQA, cross-lingual reasoning, XNLI, and even multilingual math problems, MGSM. Figure 3 shows this. So it provides a stronger foundation for building more diverse multilingual AI tools.
Got it. So it's a better base to build upon. And one last comparison. What about those models designed for one specific language, like a Chinese llama or a Japanese one? How does LLaMAX compare there?
Yeah, they looked at that too. Models like Chinese LMA2 alpaca or swallow, which is Japanese specific. The finding was interesting. While those models might be slightly better within their specific language, their translation performance wasn't dramatically better than the original LMA2. And here's the key difference. Often, when you ask those models to translate into a different language, they tend to just keep outputting their preferred language, like Chinese or Japanese, instead of the actual target language you asked for.
Oh, so they're not really translating properly?
Kind of. It's like they default back to their specialty. LLaMAX, on the other hand, reliably produces the target language you request. Tables 12, 13, and Figure 7 really highlight this. It shows LLaMAX has genuinely superior multilingual translation capability, not just single language enhancement.
That distinction is super important. And you mentioned the code and models are available.
Yep, they've released them publicly, which is fantastic for the research community, and anyone wanting to build on this encourages more exploration.
Definitely. Okay, so let's wrap this up. To recap the key takeaways for you listening, LLaMAX is a pretty big step forward for multilingual LLM translation, especially for those low-resource languages that often get left behind.
Right. And it achieved this through some really smart, even counterintuitive design choices. Sticking with the original vocabulary, not expanding it.
Yeah, that was surprising. And then using that clever dictionary-based data augmentation to create pseudo-parallel data.
Exactly. And crucially, it did all this without hurting its general abilities in English. And it actually provides a stronger base for building future multilingual applications.
It really feels like a significant step towards, I don't know, a more globally accessible AI, right? Bridging those language gaps, making information more democratic.
Absolutely. It connects to that bigger picture. Which does raise an interesting question, doesn't it?
Go on.
Well, if LLaMAX, an open source model using clever techniques, can outperform a giant like GPT-4 in specific important areas like low resource translation, what other areas of AI might be ready for this kind of specialized open source innovation? Where else could models designed with deep insights into specific problems rather than just aiming for massive scale really punch above their weight against the generalist giants? How might that continue to change the AI landscape for you?